The animals most deformed by inbreeding, when incest wreaks revenge on entire species. This is the hidden history, largely unknown, that has determined the destiny of whole bloodlines within the silent, secluded farms of rural America. For years, the practice of breeding closely related animals has pushed magnificent species to the edge of functional extinction, producing anomalies so severe they challenge our very comprehension of nature. Our story begins in 1953, deep in the isolated mountains of Western Virginia. It was here that the Peterson family managed one of the largest Appaloosa horse operations in the United States. The family patriarch, Harold Peterson, a man of limited vision but firm beliefs, was convinced he could refine the breed through what he termed blood purification, the systematic mating of close kin to lock in desirable traits. Back then, the understanding of genetics among rural breeders was incredibly primitive, explains Dr. Leonard Mitchell, a historian of veterinary medicine at Cornell. Many held the belief that crossing close relatives would amplify an animal's finest qualities, completely oblivious to the devastating biological consequences waiting to unfold. The Peterson property sat over 30 kilometers from the nearest town, nestled in a valley ringed by thickly forested mountains. This geographical seclusion gave Harold the perfect, unsupervised environment to conduct his experiments, free from oversight or interference. Visitors were a rarity, and veterinarians were seldom called, even in times of clear need. In the early days, the results appeared promising. The Appaloosas from Peterson Farm boasted stunning coat patterns, unique spots, and markings that attracted buyers willing to pay a premium. But lurking behind this apparent aesthetic triumph, a silent catastrophe was brewing. By 1958, foals began arriving with obvious deformities. Atrophied front legs, abnormally small eyes, and misshapen jaws were just the first signs. Harold, however, dismissed these as isolated birth defects and persisted with his program, now breeding animals that were themselves products of inbreeding. What we see in the surviving veterinary records from that time is alarming, states Dr. Elaine Harris, a geneticist specializing in veterinary medicine. The notes from the sole veterinarian who visited in 1960 describe foals with immune systems so compromised they'd succumb to common infections within days. Some were born with organs exposed, while others had severe cardiac defects that allowed them to live only a few hours. The situation spiraled downward rapidly between 1960 and 1963. Adult horses started displaying abnormal behaviors. Some turned inexplicably aggressive, while others developed repetitive movements, shaking their heads non-stop or walking in circles for hours. The mares found it increasingly difficult to conceive, and when they did, they frequently miscarried or rejected their newborns. The Peterson horses might have faded into history as just another sad, unrecorded footnote in American animal husbandry, were it not for Raymond Foster. He was a young National Geographic photographer who ventured into the region in 1964 for a project on the Appalachian Mountains. Foster ended up at the property by chance after his Jeep broke down nearby, says John Harrison, a local historian and author of Secrets of Rural Breeding, The Untold Stories. What he witnessed would forever alter our comprehension of inbreeding's impact on animal populations. The photographs Foster took, though never published by the magazine due to their disturbing nature, captured the outcome of 11 years of systematic inbreeding: horses with deformed skulls, misaligned jaws preventing proper eating, atrophied limbs, and skin with bald patches. More striking were the eyes. Many animals suffered from microphthalmia, a condition where eyes don't fully develop, or anophthalmia, the complete absence of eyes. What Foster documented was the total collapse of a genetic line, says Dr. Paul Whitman, a geneticist at the National Institute of Animal Health. Records indicate that by the time of Foster's visit, roughly 78% of the adult animals had some visible deformity, and the foal mortality rate had hit nearly 90%. Yet Harold Peterson seemed incapable of seeing his own role in the disaster. Personal diaries discovered after his death show he blamed external factors, the quality of the water, or even supposed radiation from nuclear tests out west. It never crossed his mind that his own breeding practices were the cause of the devastation. Be sure to check if you're subscribed to this channel so you don't miss any of the stories that uncover the darkest secrets of human meddling in nature. These are truths few dare to confront, but we all must know them to avoid repeating the same ruinous errors of the past. When Virginia state veterinary authorities finally stepped in at the Peterson property in March 1965, they found a situation even graver than Raymond Foster's photos had implied. Out of the 143 horses originally on the farm's books, only 67 were still alive. And of those, merely 12 were deemed to be in a condition meeting basic animal health standards. The official report contained descriptions that shocked even the most hardened vets, explains Dr. Margaret Wilson, who accessed state archives during her research for the Agriculture Department. There were horses with duplicated organs, incomplete digestive tracts, and skeletal malformations so extreme the animals could barely stand. One of the most emblematic cases documented was that of Midnight Star, a 4-year-old stallion who was Harold Peterson's pride. The animal, a product of 5 generations of inbreeding, had a black coat with perfectly symmetrical white spots, the very trait Peterson had selected so intensively for. However, Midnight Star suffered from a rare heart condition. His heart had only 3 functional chambers instead of 4, leaving him in a perpetual state of hypoxia and fatigue. The case of Midnight Star perfectly exemplifies the core problem with intensive inbreeding, says Dr. Thomas Reynolds, a veterinary geneticist. Harold selected solely for the visible coat pattern, not understanding he was simultaneously concentrating deleterious recessive genes that would normally stay hidden in a genetically diverse population. The science behind this disaster is complex, but the principle is clear. When closely related animals reproduce, the likelihood of offspring inheriting 2 identical copies of a gene skyrockets. If those genes carry harmful mutations, something common in every species, the result is the appearance of diseases and abnormalities that would otherwise remain dormant. In healthy populations, these damaging genes are diluted by genetic diversity, explains Dr. Harris. Think of it like a deck of cards. With a full deck, your chance of drawing the same specific card repeatedly is small. But if you remove most cards, leaving only a few suits, your odds of drawing the same card over and over increase exponentially. That's what happens with problematic genes in inbred populations. Lab tests on the surviving horses revealed alarming levels of homozygosity, the state where an organism has identical copies of a gene on both chromosomes inherited from its parents. While healthy horse populations typically have homozygosity rates between 3% and 10%, the Peterson animals showed rates between 42% and 68%. With homozygosity levels that high, it wasn't a question of if genetic problems would emerge, but how many and how severe they'd be, says Dr. Whitman. The immune system, embryonic development, metabolism, all fundamental biological systems were compromised. The effects of inbreeding weren't limited to physical deformities. Veterinarians noted deeply disturbed behavioral patterns. Mares systematically rejected their foals, an extremely rare behavior in healthy horses. Other animals engaged in self-harm, biting their own flanks until they caused serious wounds or repeatedly banging their heads against stall walls. What we were observing was the collapse not just of the physical form, but of neurological systems, explains Dr. James Bradford, a neuroscientist who later studied preserved brain tissue from the Peterson horses. Post-mortem analyses revealed significant malformations in the hippocampus and other brain regions crucial for instinct and emotional regulation. One of the most tragic aspects of the Peterson case was the prolonged suffering imposed on the animals. Harold, unable to accept that his own methods were the problem, refused to euthanize even the worst cases. Records show many severely deformed animals were kept alive for years, incapable of performing basic natural behaviors like running, grazing properly, or interacting normally with others. The Peterson case wasn't just a genetic disaster, it was a monumental ethical failure, says Dr. Elizabeth Morgan, a veterinary ethicist. By prioritizing his distorted vision of purity over animal welfare, Harold created a living hell for those creatures. Investigations revealed that Peterson had been systematically falsifying pedigree records to sell inbred foals as if they came from diverse lines. Between 1955 and 1963, he sold roughly 200 horses to farmers and breeders across at least 12 states, spreading compromised genes through a significant portion of the national Appaloosa gene pool. The impact of the Peterson case extended far beyond that isolated farm, explains Dr. Mitchell. For decades after the intervention, Appaloosa breeders across the country kept discovering genetic anomalies that could be traced back to Peterson's animals. Some of these mutations persist in the breed to this day, though at much lower frequencies thanks to deliberate diversification efforts. While the tragedy of the Peterson horses was unfolding in the Virginia mountains, an equally alarming, though less documented, situation was playing out in Clearwater County, Idaho. There, in the dense forests bordering the Clearwater River, an isolated community of farmers dedicated to breeding hunting dogs perpetuated practices that would have devastating consequences for generations of animals. The story of the Clearwater dogs remained largely unknown until 1971, when a newly graduated veterinarian from the University of Idaho, Dr. Sarah Jenkins, took her first job in the region, according to Michael Stevens, author of Lost in the Forests: The Forgotten Communities of the American Northwest. What she found would change her career and our understanding of inbreeding's effects on domestic canines. The Clearwater community had been established in the 1920s, mainly by families seeking distance from the growing urban development after the First World War. Living off hunting, fishing, and subsistence farming, they developed a culture deeply tied to the surrounding wilderness. Central to their survival was hunting, for which they heavily depended on specialized dogs. Over the decades, they developed what they called the Clearwater Hound, which local residents claimed possessed superior tracking skills, particularly for bear and mountain lion. The exact origins of the Clearwater Hound are hazy, explains Dr. Robert Thompson, a canine historian and geneticist. Fragmented records suggest an initial mix of bloodhound, plothound, and possibly American foxhound. What we know for certain is that from about 1940 onward, the region's dog population became extremely inbred, with new genes rarely introduced. The community, proud of its local dogs, firmly resisted bringing in outside bloodlines. A notebook found in Elmer Jenkins's old cabin, one of the region's most respected breeders, revealed a detailed crossbreeding system that explicitly favored mating between siblings, half-siblings, and cousins. The few dogs brought in from outside were rarely integrated into the main breeding program. When Dr. Sarah Jenkins arrived in 1971, she found a canine population in an advanced state of genetic collapse. In her professional diary, later published in the Journal of Veterinary Ethics, she documented, "The Clearwater hunting dogs display the most alarming set of congenital anomalies I have ever witnessed. Approximately 60% of pups are born with cleft palates, while nearly 80% develop severe hip dysplasia before age 2. The most disturbing is what the locals call Clearwater eye, a condition where the eyes are progressively covered by an opaque membrane, leading to complete blindness around age 4. Examining the population more closely, Dr. Jenkins found that virtually all 287 dogs in the community could trace their lineage back to just 6 founding animals from the 1930s. The coefficient of inbreeding, a mathematical measure of kinship, reached astronomical values of 43% to 51%, when values above 10% are already considered concerning in canine populations. With each generation, conditions worsened. Dr. Jenkins documented litters where over half the pups had cryptorchidism, undescended testicles, spinal issues, and severe heart malformations. Even more alarming was the rising incidence of abnormal behaviors. Younger dogs exhibit profoundly disturbed behavioral patterns, she wrote. Many develop compulsive fixations, like endlessly chasing their own tails or licking objects until they cause wounds on their tongues and gums. Cases of sudden, unprovoked aggression have become common, even in previously docile animals. More worrying is the growing tendency of mothers to reject, or in extreme cases, attack their own pups. I see it in the vacant eyes of these animals, they carry the genetic weight of decades of wrong choices. If you're watching and feel the same outrage I do, leave a comment. Nature deserves respect, not this kind of interference. We need to make this message echo so stories like these aren't repeated. Despite the scientific evidence Dr. Jenkins presented, the community initially resisted her recommendations to introduce genetic diversity. Elmer Jenkins, no relation to the vet, then 76 and considered the leading local authority on dog breeding, argued that diluting Clearwater dog blood would ruin their special hunting abilities. What we see here is a recurring pattern in inbreeding cases, says Dr. Morgan. Breeders often develop almost mystical beliefs about the purity of their lines, attributing extraordinary skills to animals that are actually severely compromised. It's a form of circular thinking where any distinctive trait, even deficiencies, is interpreted as proof of exceptionality. The situation reached a critical point in 1973 when a particularly affected litter was born on the community's central property. Of the 9 pups, 7 were born with partial anencephaly, a fatal condition where parts of the brain and skull don't fully develop. The 2 survivors developed such erratic and potentially dangerous behaviors that they had to be euthanized before 6 months old. This event finally broke the community's resistance, and with the reluctant permission of its elders, Dr. Jenkins implemented a genetic rehabilitation program. She gradually introduced healthy outside bloodlines while meticulously maintaining pedigree records to prevent further inbreeding. Dr. Jenkins's program represents one of the first documented genetic rescue efforts in a canine population, says Dr. Thompson. Her meticulous notes on the recovery process provided a model later used in several similar cases worldwide. The genetic recovery of the Clearwater dogs was long, methodical, and often frustrating. Dr. Jenkins faced not only biological challenges but also the persistent cultural resistance of the community's oldest members. Her professional diary reveals the complex dimensions of the work. April 1974. "Today I witnessed something that gave me hope for the first time in months," she wrote. Ruby's litter, the result of crossing with the bloodhound brought from Boise, produced 7 pups, all seemingly free from the cranial malformations that had become almost universal here. More significantly, I saw Elmer Jenkins, the most resistant to my intervention, smiling as he watched the pups nurse vigorously. A rare behavior in recent litters. A small step, but perhaps a turning point. The recovery program followed principles that, while theoretically known, had rarely been applied so systematically to an isolated canine population. The strategy had 3 main parts: controlled introduction of new breeders, genetic mapping to avoid new inbreeding, and rigorous monitoring of physical and behavioral traits. Dr. Jenkins's approach was notably sophisticated for the time, says Dr. Catherine Miller, a conservation geneticist at the University of Colorado. Without access to modern genetic sequencing, she created a diversity scoring system based on observable traits and known genealogy. She was essentially practicing advanced population genetics using only clinical observation and meticulous record-keeping. During the first 2 years, 14 unrelated dogs were introduced, carefully selected to preserve valued functional traits like keen scenting ability and physical stamina while diversifying the gene pool. Dr. Jenkins insisted on detailed records for each birth, thoroughly documenting physical characteristics, examination findings, and behaviors. The initial results were encouraging but not without complications. The 3rd generation of crosses showed a significant drop in the most severe physical anomalies, with cleft palate incidence falling to about 12% from the previous 60%. However, behavioral problems persisted, particularly tendencies toward hyperactivity and socialization difficulties. Clearwater taught us a crucial lesson about genetic recovery, explains Dr. Thompson. Some traits, especially those related to complex neurological systems and behavior, can remain compromised for generations after the initial gene pool diversification. This is because many behavioral traits are polygenic, controlled by multiple genes that can stay compromised even after initial interventions. A particularly challenging moment came in the winter of 1976, when a severe snowstorm isolated the community for nearly 3 weeks. During that time, 2 of the main outside breeders died in an accident when a shed roof collapsed under the snow. This event threatened to undo some of the progress, but it also showed the community's growing commitment to the program. February 1976. "I was genuinely moved today," Dr. Jenkins wrote. "After losing Rex and Sadie in the shed collapse, I feared we'd have to backslide out of necessity. Instead, Thomas and Gerald Jenkins, Elmer's nephews, traveled 42 miles through the snow to reach the nearest phone and contact breeders in Lewiston. They returned 5 days later with 3 new unrelated dogs. The community met to cover the substantial costs. The old ways die with us," said Gerald, "but the new ones will live with our children." By around 1980, the program's results were undeniable. Clearwater's canine population had grown to roughly 350 animals, with inbreeding coefficients reduced to an average of 8.3%, still higher than ideal, but dramatically better than the average 47% recorded in 1971. More importantly, the dog's functionality as hunting assistants had not only been preserved but significantly improved. What the Clearwater community discovered to its surprise was that the new dogs were superior hunters, says Stevens. With better vision, greater stamina, and more stable temperaments, they consistently outperformed the remnants of the old lines in every practical aspect of hunting. This was probably the most convincing factor for the community's most skeptical members. Clearwater corneal dystrophy, which had once condemned nearly all dogs to progressive blindness, became relatively rare, affecting less than 5% of the population. Severe skeletal abnormalities were reduced to levels comparable to normal canine populations. More significantly, abnormal behaviors like self-harm and impulsive aggression decreased dramatically. Dr. Jenkins's work in Clearwater was finally published in the prestigious journal Genetics and Animal Conservation in 1982, bringing international attention to the case. Her article, Genetic Recovery in Isolated Canine Populations, the Clearwater Model, became required reading in veterinary medicine and genetic conservation programs. The most important legacy of the Clearwater case wasn't just the dogs saved in that one community, concludes Dr. Miller. It was the practical demonstration that populations severely compromised by inbreeding can be recovered with methodical, patient intervention. The principles Jenkins established have since been applied in various situations, from working dog breeds on the brink of functional extinction to wild populations isolated in fragmented nature reserves. This scientific legacy, however, doesn't diminish the reality of the suffering those animals endured for decades before the intervention. As Dr. Jenkins herself wrote in her final reflections, every documented malformation, every observed abnormal behavior represents a sentient life experiencing unnecessary pain and confusion. The true triumph will be when such interventions become unnecessary because we finally understand that diversity isn't just statistically desirable, it's ethically imperative. While the cases of the Peterson horses and Clearwater dogs might seem like relics from a less enlightened past, the uncomfortable truth is that similar practices continue in various contexts of contemporary animal breeding. The lessons of these historical cases remain starkly relevant in the 21st century. The phenomenon we see today is more insidious because it often hides under the cloak of preservation or racial purity, explains Dr. Elena Rodriguez, an expert in animal welfare and breeding ethics. In many modern dog breeds, for example, alarming inbreeding coefficients are normalized in the name of arbitrary aesthetic standards. One of the most emblematic modern cases involves the English Bulldog, a breed whose gene pool has become so restricted that recent genomic studies suggest its current genetic diversity is equivalent to what would exist if only 68 unrelated dogs had founded the entire modern breed. Though there are thousands of bulldogs, their genetic material is so similar they effectively represent a much smaller number of unique individuals. The modern bulldog is essentially a walking cautionary tale about the dangers of inbreeding, says Dr. Whitman. Virtually everyone suffers from severe brachycephaly, leading to chronic breathing problems so serious many airlines refuse to transport them due to the risk of death during flight. Over 80% need C-sections to reproduce because selection for large heads and wide shoulders has made natural birth impossible. The genetic consequences of inbreeding aren't limited to specific breeds or species. In the dairy cattle industry, the situation has become particularly alarming. A 2019 study revealed that 99% of Holstein bulls used for artificial insemination in the United States can trace their lineage back to just two founding animals from the 1960s. The Holstein situation is a perfect example of how economic pressures can accelerate genetic disasters, says Dr. Frank Anderson, an expert in production animal genetics. Intensive selection for milk yield has produced cows that give impressive quantities, over 30,000 liters compared to a typical 1950s cow's 5,000, but with devastating consequences for longevity, fertility, and welfare. Modern Holsteins typically survive only 4 to 5 years in production, compared to a natural life expectancy of 15 to 20 years. Fertility problems have become so common that many farms consider it normal for a cow to need 3 to 5 inseminations to conceive, when historically 1 or 2 were enough. What we're witnessing is a form of genetic extremism, continues Dr. Anderson. We're essentially creating animals that are efficient short-term milk production machines but fundamentally dysfunctional as complete biological organisms. The case of show Arabian horses represents another worrying contemporary example. Selection for extreme facial characteristics, particularly the concave profile known as dish face, has resulted in a population where neurological, respiratory, and dental problems are common. Some of the award-winning Arabians in major shows have such extreme cranial malformations they would have been considered severe deformities just 50 years ago, explains Dr. Wilson. We see animals with nostrils so small their respiratory capacity is dramatically limited, and facial profiles so concave they cause chewing problems and dental malocclusion, all in the name of an aesthetic standard taken to the extreme. Perhaps even more disturbing is the silence that often surrounds these issues. Breeders, show judges, and breed associations frequently minimize or completely ignore the genetic consequences of these practices, focusing exclusively on the aesthetic traits valued in the show ring. There's a conspiracy of silence in the world of animal breeding, says Dr. Howard Bennett, a veterinarian and former dog show judge who has become a vocal critic of modern practices. Behind the scenes, everyone recognizes the problems. We see puppies dying from heart defects, adults who can barely breathe, and animals developing devastating neurological conditions. But publicly, we keep rewarding the most extreme specimens, perpetuating the cycle. In the context of wild animals and conservation programs, the lessons from Peterson and Clearwater take on added importance. When populations of threatened species are reduced to critically low numbers, the risk of inbreeding depression becomes a major challenge for recovery efforts. The case of the cheetah, Acinonyx jubatus *, dramatically illustrates this. Genetic studies show the world's cheetah population has gone through at least 2 severe genetic bottlenecks, periods when the population was reduced to such low numbers that genetic diversity was drastically diminished. Modern cheetahs have such limited genetic diversity they're practically clones of each other from an immunological standpoint, explains Dr. Samantha Lewis, a conservation biologist. This means a single infectious disease could potentially decimate the entire population, as all individuals share the same immune vulnerabilities. It's like having a human population where everyone has exactly the same blood type and the same allergies. This genetic homogeneity manifests in alarming reproductive problems. Over 70% of male cheetah sperm have morphological abnormalities, and semen quality is consistently low. Females often produce small litters, and cub mortality is significantly higher than in species with greater genetic diversity. What we see in the cheetah today is the result of natural inbreeding forced by population reductions, continues Dr. Lewis. But the worrying thing is that we're deliberately creating similar situations in captive populations of other threatened species when we don't adequately manage genetic diversity. The irony is that while the negative effects of inbreeding are well documented and scientifically understood, practices promoting genetic homogeneity continue to prevail in various animal breeding contexts. This disconnect between scientific and practical knowledge represents one of the greatest challenges for animal welfare in the 21st century. We know better, but we often don't do better, says Dr. Rodriguez. Historical cases like Peterson and Clearwater should serve as powerful warnings, but instead we often repeat the same errors on even larger scales, now with the aid of advanced reproductive technologies. Artificial insemination, for example, allows a single sire to generate tens of thousands of offspring, something impossible through natural reproduction. When that sire carries problem genes, the negative impact is exponentially amplified through the population. In the age of reproductive biotechnology, the risks of genetic homogeneity are even greater, warns Dr. Whitman. A popular dairy bull can have its semen distributed globally and produce over 100,000 offspring. If we later discover it carries a problematic genetic mutation, the damage is already spread across multiple generations and geographies. The fundamental question emerging from these historical and contemporary cases is about ethics, responsibility, and our relationship with other species. Intensive inbreeding represents a form of human interference in the fundamental biology of other creatures that often results in unnecessary suffering. What the cases of Peterson and Clearwater teach us above all is humility, reflects Dr. Morgan. They remind us that interfering with the basic evolutionary mechanisms maintaining animal population health often leads to unintended but profoundly harmful consequences. Genetic diversity isn't a luxury or an abstract preference. It's the foundation of health and biological functionality. There are, however, signs of encouraging change. In 2019, the United Kingdom's Kennel Club implemented new breeding guidelines for English bulldogs, French bulldogs, and pugs, aiming to reduce extreme brachycephaly in these breeds. Outcrossing programs have been started for particularly compromised breeds, carefully introducing genetic material from related breeds to expand the gene pool without losing essential defining characteristics. The Moon for Dalmatians program is an excellent example of how we can address genetic problems without abandoning the concept of defined breeds, explains Dr. Thompson. A single cross with a pointer, followed by generations of breeding back to pure Dalmatians, has helped introduce the normal uric acid metabolism gene, eliminating the breed's predisposition to bladder stones while preserving its distinctive appearance. In the context of wild species conservation, sophisticated genetic management strategies are being implemented to maximize genetic diversity in reduced populations. The Mexican Wolf Recovery Program, Canis Lupus Bailei *, for example, uses advanced genomic analyses to determine optimal pairings between captive individuals, maximizing the retention of genetic variation. We're finally recognizing that preserving only numbers isn't enough, says Dr. Lewis. We need to preserve functional genetic diversity if we want these species to survive long-term. A numerically successful recovery that results in a genetically compromised population isn't really a conservation success. As we advance through the 21st century, the lessons of Peterson and Clearwater remain fundamental to our understanding of ethical responsibility in animal breeding and conservation. These stories remind us that our power to shape other species through reproductive selection carries with it the obligation to understand and respect the fundamental biological principles underpinning health and animal welfare. The true legacy of these cases isn't just in the suffering they documented, but in the lessons they offer us, concludes Dr. Rodriguez. They show us that respect for biological integrity and genetic diversity isn't just scientifically sound, it's ethically imperative. Our interventions in animal reproduction should be guided not only by aesthetic or productive goals, but by a fundamental commitment to the welfare of the animals under our care. If you've watched this far, it means you appreciated this story. Leave a comment saying I watched here so I can get to know you and see who truly enjoys the content on this channel. Be sure to subscribe to follow our investigations that reveal the darkest and most educational truths about human impact on the animal kingdom. Leave a like to support this awareness work, and share it with friends and family who need to know these important stories about the consequences of animal inbreeding. Together, we can promote a future where respect for genetic diversity and animal welfare guides our breeding and conservation practices.